Right, the wave equation. Who's not here at the moment? Matthew. Would someone, no, we know that Daniel's absent, and Daniel's collecting from, who's going to collect from Matthew? Right. Wave equation, this will take you back to grade 10. So let's clear the board, and let's have a look at the wave equation. I'm not going to spend much time on it, because this is all revision of old stuff. We'll do one or two examples. The wave equation is either written V equals frequency times lambda, or C equals frequency times lambda if we're talking about the velocity of when dealing with light. Right. We know that V is the velocity of the wave. And what's the velocity measured in? Meters per second. What is F? The frequency of the wave in hertz. And lambda is the wavelength in meters. And that is speed of light in a vacuum. And that we know is always equal to 3 times 10 to the power of 8 meters per second. There we are. You will also see another formula, which we don't really use, and that is that velocity is equal to delta x over delta t. I think in your notes it's S, am I right? Some textbooks use the symbol S for delta x. So you can please just change that. That formula is very seldom used. Okay, I'd like you to do number 1, please. Quickly do number 1. We'll read number 1. Calculate the frequency of light having a wavelength of 6 times 10 to the minus 4. The problem with that is that you're only given one value there, 6 times 10 to the minus 4 meters. Calculate the frequency of light having a wavelength of 6 times 10 to the minus 4 meters. How can you do a calculation if I've only given you one number? You automatically have C. What is C equal to, Esther? Okay, you've always got that. Okay, you should all be finished by now. You finished, Aiden? 1. Everyone finished number 1? Okay, right. Let's mark them. Okay, finish them all. Finish them all. Are you just doing them? Yeah, this is not good. Because then you're not practicing your layout properly. Where's your formula? No, do them properly in your book. Same with you, Thomas. That's good. What's that capital T? Why have I put a squiggly T on there? That's tau, which is a squiggly T, which means the period of a wave. Where have you done them? I'd prefer you to do it in your book. One more minute, then you need to be finished. Okay, let's do it. Okay. Esther, will you tell me the first one, please? Number 1. you're asked to find the frequency. What's your formula? Lambda, okay, substitute. Don't change it around first substitute. What is C? Right. Frequency we're trying to find. Wavelength. 6 times 10 to the minus 4. That's going to give me 0.5 times 10 to the 12, which is equal to 5,00 times 10 to the minus 14. Minus 11. Oh, to the plus 11, sorry. Is that correct? Unit? Hertz. Nice and easy. Good. Number 2. Let's read it. Calculate the wavelength of light having a frequency of 2 times 10 to the 5 hertz. Aidan. Yes. Right. $1,500 would be good enough. Okay. All happy? Number 3, light has a period of 2,5 times 10 to the minus 7 seconds. Calculate the wavelength. Remember that tau equals 1 over frequency. Now, can anyone tell me what do we mean by the period of a wave? What do we mean by the frequency of a wave? In a second. How many waves pass a point in a second? I want you just to stop and think of a train. Okay? Let's say we had a train, real super fast train. Okay. This train is traveling this way. And you're standing at a station looking through a narrow gap. All you can see is a narrow portion of the train, and you stand there with a stopwatch and you say, right, when this train comes, I'm going to start the stopwatch and I'm going to count how many carriages go past in 1 second. Let's say you're a real fast counter. Okay? And as the train goes past, it's moving. This train is really moving. You, 1, 2, 3. 3 trains or 3 carriages. So starting from there, 1 train, 2 or carriages, 3 carriages go past in a second. What is the frequency? The frequency would be 3 carriages per second. Do you agree? So it took 1 second, really a fast train, for 3 carriages to pass. That would be the frequency, the number of carriages, and you can think of a carriage as a wave. Okay, so it would also be the number of waves that go past in a second. How long would it take just 1 carriage to go past? How long did it take 3 to go past? 1 second. How long would it take 1 to go past? 1/3 of a second for 1 carriage. Do you agree? Now, how did you get that one? You said, what is tau? Tau is equal to 1 over the frequency, which is equal to 1/3. So tau is your period, the time for 1 complete wave to pass a point. What is the frequency? The number of complete waves that pass in 1 second. You may want to write that down. So we've got a frequency. So here are some definitions. I don't think you need to know it. Frequency is the number of waves, the number of carriages passing a point in 1 second. Tau is the period of the wave. And what is that? The time taken for one complete wave to pass a point. And lambda is the wavelength. The distance between two corresponding points on two consecutive waves. We'll have a look at that in a moment. Okay, now if these are three waves, we'll label this wave number 1, number 2, number 3, number 4. Which of these waves are consecutive waves? What does consecutive mean? One after each other. So give me two consecutive waves here. 1 and 2. Or is the one after the other? Another two consecutive waves? 2 and 3. What about 1 and 3? No. Now, who can tell me what do we mean by corresponding points? So would this point there be corresponding to which point on wave number 2? There. There. So, that is your wavelength. Okay? The distance between two corresponding points on two consecutive waves. No point having two corresponding points on two non-consecutive waves, because then that's, in this case, two wavelengths. You agree? Where else would be a corresponding point? Would that point there and that point there, would that also be a wavelength? Yes. Okay, another corresponding point. Could I choose that point there? Where's the corresponding point? There, you agree? That's also a wavelength. Okay, so you can measure it anywhere as long as they are matching points, corresponding points, and as long as they're on consecutive waves. Right, all happy with that? So the period of a wave, we abbreviated with that squiggly capital T, which we call tau. Okay, tau is the time it takes for one wave. How long does it take one wave to come past? Frequency is how many waves can you squeeze past in 1 minute or in 1 second. Okay, tau is measured in time. What will it be measured in? Seconds. This is the number of waves. This is in waves per second. which we abbreviate hertz. And this is in meters because it is distance. Okay. So now we can do number 3. Number 3, light has a period of 2.5 times 10 to the minus 7 seconds. In other words, it takes 2.5 times 10 to the minus 7 seconds, very, very small period of time, a tenth of a millionth of a second, okay, to pass. Calculate the wavelength. Well, what's our formula? C equals frequency lambda. We've got C, we're asked for lambda. We don't have F. Do you agree? So, F equals 1 over tau. What is tau? 2.5 times 10 to the minus 7. Therefore, frequency equals, what does that work out to be? Sorry? 4 million. 4,0 times 10 to the power of 6 hertz. Thank you. Now, I'm wanting to find wavelength. So substitute into this formula here. What is C? 3 times 10 to the power of 8 equals 4 times 10 to the power of 6 times wavelength. Wavelength is therefore equal to 7,5 times 10 to the power of 2. What? Okay, or 750 meters. Sorry, Yvonne. Yes, sorry. 75 meters. Yeah, I had it like that. All right. Is that to the power of 1? Don't go and spoil my brilliant reasoning here. Just going to tell you to throw your calculators away. Thank you. That's only because you had the answer there. Right, number 4. Yeah, you're using that other equation, yeah, which you're not seldom, you're very seldom going to use it. I just threw it in just so that you could get some practice. Calculate how far light will travel in 1 minute. Taylor, can you take us through that one, please? Okay. V equals delta x over delta t. What are you trying to find here? Okay, what is V in this case? 3 times 10 to the power of 8. Can I put it over 1, seeing we've got a fraction on this side? Happy? Delta x we're trying to find. Delta t is 1 minute times 60 seconds in a minute. Good. Delta x is going to be equal to 1,8 times 10 to the power of 10. Okay, right, all happy. Move on. Anyone need to leave early today? About 4:15 today. Okay, 4:45. Oh, you're going to miss out a very important part. No, we'll finish at about 1:30. Right, so, okay, grade 12s, this work that we've done now, as I said, that's all revision. Am I right? You all seen this before? You're all a bit rusty on it? I suggest for homework you actually go over it. Don't leave it for the night before the exams. You know how you feel about this work. How do you feel about these equations? No, they're easy now. What were they like in grade 10? This was your nightmare section, am I right? Yes. So as I say, those definitions, they're not going to ask you those definitions, okay? You don't have to go and learn them off by heart, but in case you need to understand them, you've got them there. Right. The last little bit of revision that we're going to finish before you go home today is the whole spectrum of light. Now, if you have a look, the way you've got it drawn in your book, you've got these long waves over here, or in your notes. Then they get shorter and shorter. And obviously they start getting very, very close to each other at this point over here, which I'm just going to draw as a mess. Okay. Imagine that they're at the same height. So we'll put in this imaginary line. I'll draw in blue. Anyone know the name of that line? Mean position. Okay, that's the line that runs through the middle of the waves over here. It's got a bit out of hand, unfortunately. This wave should have the same amplitude all the way through. Okay, so it shouldn't be a taller wave here and a smaller wave over here. All that's happened is the frequency, the wavelength, is squashed up, so that the frequency, you're squeezing more waves in a second. Okay. So you don't have to draw it, it's there in your notes. Can anyone tell me which part of this wave travels faster? The long waves travel faster because the waves are longer, you get through more. All agree? Who of you don't know? What do you say? They all travel at the same speed. Yes, thank you very much. This whole lot travels at 3 times 10 to the power of 8 meters per second. It's a light wave. Okay. So if it's all traveling at the same speed, if you've got these tiny little carriages at this part of the train, and these long stretched out carriages at this part of the train, when the whole train's joined together, it's all traveling at the same speed. Which part of the train will you get more carriages going past in a second? There, okay, higher frequency, more carriages, more waves per second. These long train carriages, you'll get very few of them going past in a second. All understand? Which part of this wave will have the longest period? It takes a long time for that wave to go past, whereas that wave goes past very quickly. Okay, right, which one's got the highest frequency? Okay, well so let's have a look at what we've got there in your notes. Let's stick to your notes. The first heading that I've given you is wavelength. We're going to have a look at the wavelengths. Tell me, which part of the wave, the left or the right, has got the longest wavelength? So these are long waves. And these are very short wavelengths. Okay, that's easy. Let's have a look at the next one, which is frequency. We've just spoken about that. Right, which part of the wave will you get more waves going past in a second? So we don't say this has got a short or a long, it's got a high frequency, and these have got a low frequency. Right, what was the next heading there? The energy. Which part of the wave's got a high energy? Why? That has a high energy, and I'll tell you why in a moment. And this has got a low energy. And if we put in another heading, velocity. What's your velocity here? 10 to the power of 8 meters per second. People tend to forget that. Three times 10 to the power of 8 meters per second. Okay. Now, you notice that these two are the same. Low frequency, low energy. You notice that? If it's got a high frequency, it's got a high energy. And the reason for that is the energy of a wave is given by the formula, E for energy equals H, that's a constant, times F. We'll talk more about this tomorrow. E equals HF. That's just a number, and that's the frequency. So you can see that the energy is directly related to the frequency. If you've got a high frequency, you've got a higher energy. If you've got a low frequency, you've got a low energy. Right. So that's a very, very important equation, which, as I say, you can write it down there now if you want to, if you like the look of it, but we will get to it at a later stage. Right, now also, you'll see in that equation that these really long waves over here, these are your radio waves. Right, those are your radio waves. And these ones over here with the high frequency and correspondingly high energy, so therefore they are dangerous. Okay, these are your gamma. We don't even talk about waves anymore now because it's becoming more sinister. We say gamma rays. Okay, right. Up there with the gamma rays, you've also got your X-rays. And then you've got your ultraviolet rays, or radiation. Now we start to notice how the terminology from gamma rays, X-rays, we don't really talk about UV rays, do we? Talk about UV radiation. Sounds a little bit more less threatening than these ray guns and things like that. And then we move down, okay, until you get your visible light over here. Now, as I told you earlier on, your visible light is actually not nearly as big a chunk of your spectrum. If this was the full spectrum of electromagnetic radiation, James, then this would probably be a narrow little gap, not even that wide. Okay, and which colors light do we have? Who could give me the names of the colors? Red, orange, green, blue, green, whatever, ending with violet. Okay, so your colors are, I'll fill the middle ones in green, red, orange, yellow, green, blue, indigo, and violet. Okay, red, orange, yellow, green, blue, indigo, violet. And they fit into that little narrow little band. And that is all that human beings can see. That little visible spectrum. There's a much bigger spectrum on either side of it. We can't see this light. We can't see that light. Because we can't see it, we don't even consider it to be light. We call it waves or rays. But it's actually light. Okay? All of this makes up part of the electromagnetic spectrum. Then we have the infrared. Okay, your infrared radiation. You have your microwaves. Now we're starting to call them waves again. Waves are nice and gentle. They make us feel relaxed. And your TV rays and waves, radio waves. What else have we got? Yeah, okay. Right, so you've got all that information on that. I don't expect you to know it. I do expect you to know the infrared. They always ask about that. Ultraviolet. I would say the ones... Yeah. Okay, you don't have to know, okay, the TV ray is fitting over there, and okay, that's not important. Just have a fairly good idea. But the important thing is that the ones with the high energy over here, these are the dangerous ones. These they say are not dangerous. We're not too sure. Where's your cell phone fit into this? Over here somewhere. Okay. The Wi-Fi would be at this range here as well. Okay. And we're living in a world which is totally contaminated with waves at the moment. Okay, radio waves. Now when we talk about radio waves, what is that? The sound that comes out of your speaker. That's sound waves. Where do you get light coming out of your radio? We spoke about it earlier this year. The waves that travel through the air, that get sent out by the broadcast stations, those are light waves. And the antennae on your radio, if you had an old radio, it would have an antenna on it. Nowadays the antenna is built into it. That picks up those light rays and converts it into a sound wave. Okay? But it's all light that gets traveled and sent through the atmosphere out into outer space if necessary. Right. That's where we're going to stop today. Tomorrow we start on with the particle theory of light and the photoelectric effect. Today we've covered the wave theory of light. Tomorrow we'll prove all of this wrong. Thank you.